So if there was ever a section that was people's least favorite, it's molecular orbital theory, and perhaps it's just the presenter. But it is really neat. What we're talking about is really trying to shift those atomic orbitals and the probabilities associated with them into molecular orbitals. And we get some pretty neat conclusions that comes out of it. And so we kind of draw from some of it. So remember that electron orbitals are really probabilities. So if we're really going to understand anything about molecular orbitals, we have to understand a little bit better about probabilities. And these probabilities roughly adjust from electrons moving similar to waves. With that, that means there's phases associated with the waves. Okay, so if we looked at, say, this diagram, we have a positive amplitude and a negative amplitude, and that's the phase associated with our orbitals. So when you think about the shading that you saw in your p orbitals, that's what's being referenced as kind of the phase of those. I wish I had a better explanation, but that's all I've got. When we talk about two orbitals interacting with each other, they can now interact or overlap, just like we've been showing, where they directly overlap or even indirectly. But there's now a question of, do they overlap in a way that allows the electrons to add to each other so they're in phase, or do they add in a way that they subtract from each other because they're out of phase? And that's what the video attempted to go through and do that you've already seen. So that's where you're seeing the positives and minuses and how they kind of contribute to either forming a bonding interaction or a anti-bonding interaction. And we don't need all those. So in our sigma system, if we were to look through that again really, really quickly with our s orbitals, our atomic systems come in with just these p orbitals or the s orbitals. And those can interact in a way that generates a molecular bonding orbital or a molecular anti-bonding orbital. And it's not a not bonding orbital. And that becomes one of the kind of interesting statements within this. Putting electrons there also doesn't mean that we don't have bonds. It just means the overall picture for that molecule existing or that molecular system is less favorable than one that didn't have antibonds. What we're looking at for our atomic system is really the non-bonding. Okay, that's our baseline energy because it's not contributing to bonding. If we're lower in energy than our non-bonding system, our atomic orbitals, then what we would have is a bonding interaction. If we're higher in energy, well, now we're saying we're going against kind of normal stabilities. That's why we enter anti-bonding. The interactions that come out of these are also going to contribute to that sigma and pi nomenclatures referencing that we looked at in hybridization theory. So if we're going to look at these two atomic orbitals coming near each other, they're definitely going to get to the same distance from each other always. Okay? In a bonding situation, those orbitals overlap favorably, meaning they're in phase, which means we increase the probability of finding the electrons between the nuclei, hence a larger shading in there, or a larger space is found in there, as opposed to the individual s orbitals that had initially made them up. Okay? In the anti-bonding system, the electrons are now not located in between the atoms. They're being pushed away. Again, our s orbitals are coming into roughly the same location, but because of how they're interacting or overlapping in a negative sense or a counterintuitive sense, not counterintuitive, counteracting sense, we see the electron orbitals kind of push opposite each other. Big conclusions that come out of this. So number one, if we're getting the orbitals directly overlapping, as we're seeing with our s orbitals, this direct overlap is what is known as sigma bonds. The direct overlap allows rotation because as we rotate, we don't see a loss of overlap of those orbitals. So we've got that direct sigma interaction. When we move to the anti-bonding state, it's still a direct overlap, but it's a deconstructive overlap. And that's So it's still going to be called sigma, but now we have to acknowledge the anti, and that's where we get the star. If I want to look at the molecular orbitals of bringing these two atomic orbitals near each other, those molecular orbitals are now represented here. And where our atomic orbitals were SPD, etc., now what we're looking at is this new kind of mixing of the atomic orbitals. And in this case, because I'm overlapping two s orbitals for anything that had just s orbitals interacting, we would have to generate two molecular orbitals because we're starting with two atomic orbitals. Those two atomic orbitals could add in a constructive fashion, thereby being bonding, or they could add deconstructively, and we get the anti-bonding orbital. So every atomic orbital generates a molecular orbital. Okay? So if you have 3 atomic orbitals, you're getting 3 molecular orbitals. That's how it works. Okay? We can't lose them. The part that's going to come into play is then deciding how we split between bonding and anti-bonding. Well, every bonding generates an anti-bonding. So if you have 3 molecular orbitals, well, one will be bonding, one will be anti-bonding, and that third one will now be non-bonding in between, right? Because they have to space out evenly within it. And that's largely the extent that we really want you to get out of it, particularly for the sigma type systems. Okay? We can move to, the p type or pi type orbitals, and this would be more reserved for kind of linear commutation or combination of atomic orbitals or frontier molecular orbital, neither of which we really dig into here. But we can get the same kind of idea on how we'd bring this together. If we look at these orbitals aligning on the x-axis, well, the x orbitals, p orbitals would come together, nuclei, nuclei. We would see the p orbitals come together in kind of an additive fashion on the x-axis for our px. This is what we're overlapping. Or they could have come together in a way where they were kind of deconstructive. Note that as we do this, we see nodes or places where our electrons can exist. Our atomic orbitals in this case each came in with a node, so our lowest energy is going to be with 2 nodes. When we go up in energy, what happens? We get an extra node. Right? 3 nodes versus 2 nodes, and that's where those electrons can't exist. Right? That's what those nodes are referencing. In the bottom case, we're looking at a direct overlap again. So even though these are p orbitals, that direct overlap is really what's getting us the sigma, and then our sigma antibonding above. If we try to go through and look at the py and the pz, same idea on where those orbitals come into play. There's our py and our py. They never directly come in contact with each other, but as long as they're in the same plane and they have the same shading, okay, we could see those electrons jump across. And this is where we could see orbitals where we have this big long thing. This is now an indirect overlap, and that's where we're getting the pi term from. They could have just as easily overlapped the other direction. Okay, so now we have that node and that node. 2 nodes, 1 node. Pi star, because we don't allow that bonding interaction happening in between. Right? That's kind of the intent behind it. We'd see the similar thing happening for the PZ in this case, and the PZ is going to have the same type of interaction as the PY, so it's going to be equivalent in energy. So if we were to go through and look at kind of a molecular orbital diagram for this, we would have a sigma bonding, we would have 2 pi bonding, 2 pi antibonding, and 1 sigma antibonding. Depending on the exact energetics and electronegativities of the individual atoms, you can see these pi orbitals slide either above the sigma star and below the sigma, depending on those individual energetics. I don't expect you to know that, so don't stress about that. What I do want you to understand is how these things can interact with each other, and that's going to be our primary focus. Okay, so don't dig too deeply into this. Where it becomes relevant for our sigma and pi is that if we were looking at our sp orbitals, they're just like our p orbitals. So we could either be phased that way or we could be phased that way. And then again, how those interactions come into play. We either get them directly overlapping, in which case we get a bonding interaction, or they deconstructively overlap and we get that anti-bonding interaction. So if we were to draw that kind of pictorially, here constructively overlapped, unshaded to unshaded, or we could do shaded deconstructive overlap. Okay, so we would end up with a node there, node there, node there, node here, and node here. The pictures that kind of come out of these would be something along these lines with a little ball at the other end, or balls and balls, okay? With the center being our nucleus and our node, okay, roughly. The idea is just to understand that there is a constructive and deconstructive overlap. It's going to become much more relevant when we move into second semester and we look at pi systems, because in pi systems we can now talk about all the different molecular orbitals for the pi bonding systems. We will actually look at it when we look at spectroscopy in the next unit with UV vis spectroscopy, because we're concerned about how multiple p orbitals interact with each other. For instance, if we had a pi system like this, what we're talking about would be how do these double bonds interact with each other? And hopefully what you remember already from your practice is that we have the ability to do resonance, which means the pi system is all interacting with each other. So there's multiple different ways that we could generate molecular orbitals. They could all be in phase, which would be an exceptionally low energy state. We could then increase the energy by adding a node. That node causes an increase, horribly drawn there. Just kind of get rid of all of that. And we'll end up with 4. We know we have 4 because we have 4 atomic orbitals. Whoops, and of course I colored in the wrong one. And where this becomes useful for us is we can see these nodes up here. We have technically one node through the middle, but we'll call it 0 because we started with p orbitals. 1, 2, and 3. And where this becomes interesting or useful is that if we're talking about UV vis spectroscopy, we're talking about electrons jumping orbitals, going up in energy. This is where we got our atomic line spectra. But we can do it for molecules too. If we now have these as our molecular orbitals, we can talk about this being a pi interaction, pi star, pi star. How do we know that 3 and 4, our p orbitals 3 and 4, are anti-bonding? Well, look at the nodes. There's 2 nodes, okay, which means anti-bonding, and 1 bonding interaction. The bottom one, they're all bonding. The pi energy, or P2, 2 bonding, 1 anti-bonding. Right? Anti-bonding, 2 anti-bonding, 1 bonding, all anti-bonding. So by referencing those nodes, that can help us label whether they're bonding or anti-bonding. If we're going to look at spectroscopy, we're going to talk about electrons jumping from one level to another, and we could then use that to determine something about the energetics of the individual orbitals. And that's kind of neat. It also allows us to identify compounds and all sorts of neat stuff like that. That's ultimately where it's coming from. We can use this with our molecular orbital diagram. Remember, we showed in our hybridization how we could get those hybridized orbitals. We could generate molecular orbitals out of this. I don't want you to get too kind of crazed out in this. So let's go through and look at the molecule first and then kind of decide what we're expecting. Because you might be seeing this and going, oh my God, I have to draw all these pictures of all the things and the orbitals and the nuts and the bolts. And no, not at all. okay? What I want you to be thinking about is what kind of things would you expect to see in this interaction? So to start this off, C2H4, we would have to consider all the atomic orbitals that went in. Well, each of the hydrogens brings in one atomic orbital. So the hydrogen has one, but there's 4 of them. Carbon brings in 4 atomic orbitals, but there's 2. So we're looking at 8 and 4 is 12. So we have 12 atomic orbitals. That's that referencing. Okay, what were those orbitals that we brought in? Hydrogen again, 1s. The hydrogen or carbon brought us 2s and 2p, but there's 3 2p's. Okay? What does this mean for our molecular orbital diagram? Okay? Well, if I have 12 atomic orbitals, I better have 12 molecular orbitals. So now the question is, how does that split out? Well, because I know for every bonding interaction there's an anti-bonding, I can look at a bonding type and an anti-bonding type. Because I know they split evenly, I know there must be 6 anti-bonding and 6 bonding. Okay, that's pretty straightforward. Could we nuance out the bonding into the different categories? Because that bonding is going to have sigma and pi bonding interactions. Okay, well, how would I figure that out? Well, remember, sigma begins with S, just like single begins with S. So when we go through and evaluate this, I've got 1, 2, 3, 4, 5 sigma bonds. So I'm going to have 5 sigma bonding interactions, and I will have 1 pi bonding. How is that going to break down in our antibonding? The exact same way. 5 sigma antibonding and 1 pi antibonding. Okay, that's it. That's the image. So if we do the big reveal behind this, that's all we're asking for. Ta-da! There it is. Okay. The part that's going to be most relevant to us is what we just addressed on the previous slide. We're talking about taking our highest energy electrons, which are going to be in the pi. Why would our pi be higher in energy than our sigma? Well, pi involve p orbitals. P orbitals are higher in energy than sigma. There we go, because it's s orbitals. So those electrons are now going to be our highest energy electrons. So if I'm going to look at how this molecule interacts, I'm going to look at the highest energy electrons because they're the most likely ones to interact with another molecule because they're the highest in energy. So the picture can help me kind of reference that. The next thing we could do would be, well, how would I get them to move up to that energy? Well, I would have to hit it with light. What light would I have to hit it with? Well, ultraviolet light. Okay? That's UV vis spectroscopy. That's the point. We're taking those electrons from that highest occupied orbital. Okay? That highest occupied orbital is the most important to us because those are our highest energy electrons. Well, that orbital is a molecular orbital, so we could call this the HOMO, or the highest occupied molecular orbital. Where are those electrons most likely to jump to? Well, they're going to jump to the lowest energy unoccupied orbital. And this is where we now introduce the LUMO. And so you'll hear reference to HOMO and LUMO a lot. And all we're really saying is, how do I get the highest occupied electrons to go to the lowest unoccupied orbital? Okay? That happens to identify a molecule. If I want to run a chemical reaction, I need to take the highest occupied electrons and transfer them to the lowest unoccupied of my reactant. Okay? And if that transition isn't favorable, well, then the reaction doesn't happen. Okay? The logistics of that are very energetically loaded, and you don't need to know that. So don't stress about that. Okay? I just want you to be aware of that concept. And if you happen to do more studying in organic chemistry, in particular physical organic chemistry, you can dig into frontier molecular orbital theory, and then you can come back and teach me about it because I think it's cool and I want to learn more. Okay? But that's really what you're trying to get out of the molecular orbital theory. Identify your HOMO, your LUMO, anti-bonding, bonding, how many molecular orbitals should you have, what do they roughly look like, kind of cartoons. And that's it. You don't even have to rank them really yet as far as our cartoons. The pi ones you do, okay, because those are a little bit more straightforward. Okay, we could do it with the C2H2 as well. In fact, let's just do it. We got our molecular orbitals and our atomic orbitals and our molecular orbitals. C2H2. What do we need to evaluate? Well, hydrogen comes in with that 1. There's 2 hydrogens plus our 4. There's 2 carbons. That's 8. 8 and 2 is 10. So we need to account for 10 molecular orbitals. Did I count that right? I think I did. In that, bonding orbitals, we're going to have 5 and 5 anti-bonding. How are those going to split out? Well, for our sigma, we have 2 sigma, and for our, I think I counted something wrong. And for our pi, we should have 2 pi, gets me 4. 8, 2. Dang, what did I miscount? Well, crap, I'm just going to have to leave it at that. Oh, there's 3 sigma, dude. For those of you wondering, 1 sigma, 2 sigma, 3 sigma, there's my miss. And then for the 5 anti-bonding, I would get 3 anti-bonding sigma and 2 anti-bonding pi. Okay? That's the basics behind what you need to be identifying. Okay, so don't stress a whole lot about it. Just identify where those kind of parallels are. You should be fine. Okay, so our big summary of molecular orbital and hybridization theory. A lot of this big summary ties back to hybridization. So sigma and pi. There's no more single, there's no more double. Sigma bonds are effectively single bonds. Rotation, not important. I can rotate as much as I want and it doesn't change the molecule. That becomes a lot or very, very challenging for you because a single rotation can make the molecule look drastically different, and it's not. It's really the same thing. The pi involve your p-type orbitals. These are multiple bonds. Okay? So if you're saying double, triple, those are due to pi bonds being stacked on top of a sigma. As soon as you have a pi bond, you lose rotation. And that's because if you start to rotate, you lose that overlap, right? You lose that overlap of those orbitals, and electrons don't like that. So they prevent that rotation. Okay? It's not technically impossible, but you have to break the bond to allow the rotation to occur. The next one is dealing with hybridization. Right? Increased hybridization means more orbitals are involved. The more orbitals you bring into it, you move that hybrid orbital to a higher energy. Why? Well, the orbitals you're bringing in are more p orbitals. More p orbitals mean higher in energy because p orbitals are higher than s. Right? If we push that even further and did d orbitals are even higher. So those hybrids would be even higher than that. And we also see lower electronegativity. Why is that? P orbitals are slightly larger than our s orbital. Okay? Because of that, the electrons are held further from the individual atom. That's effectively less electronegative because your electrons aren't as attracted to the center atom, which is the flip of how we talked about it in our past video. Okay? But it comes to the same conclusion. So those are our big conclusions that you absolutely have to have nailed down. The exact details of how and why you've got those nailed down kind of comes up to you. And then I just want to throw this in because I think this is kind of neat. If we were to look at the molecular orbital of a carbon-chlorine bond, okay, and in particular we're looking at the carbon of methane. Our carbon is coming in as sp3 hybridized, the chlorine is sp3 hybridized. So we'd be looking at kind of the sp3 hybrid dynamic. If we were to make a bonding interaction, those electrons would be found closer to between the atoms, and we'd have the little nodes on the outside. Okay? Those nodes are carryovers from our atomic orbitals. If we looked at the antibonding interaction, we would see another node appear in between. Right, there's our nucleus. And then our node. So we have our sigma antibonding and our sigma bonding. If we're looking at the bond between the carbon and the chlorine, well, the carbon brings in 1 electron, the chlorine brings in 1 electron. Those 2 electrons would go into the bonding interaction, and we would now have a bond between the carbon and the chlorine. Right? Remember what I talked about. We need to get our electrons to go from a highest occupied to a lowest unoccupied. It turns out that the carbon-chlorine bond, right, or this particular molecule, is particularly susceptible to atoms attacking the carbon. Okay, why might that be the case? Well, chlorine is more electronegative, partially negative, the carbon partially positive, so we would expect the electrons to come in towards that carbon. So this molecule acts as an electron acceptor. For it to accept those electrons, it would have to go into an empty orbital. Well, where's the empty orbital? The empty orbital is the antibonding orbital. Where's the majority of the orbital located? It's located on the backside of the carbon-chlorine bond. Which means if I'm going to predict how a molecule, okay, let's call it a reactant, with electrons come in to react with a carbon-chlorine structure, I'm going to expect those electrons to come into the backside of the bond because that's where there's the largest orbital space on the carbon to create an overlap to form a new bond and to thereby break the carbon-chlorine bond. Molecular orbital theory puts that potentially out there in the world. When we move into Unit 3, what do we end up seeing? That's true. Right? If we're going to look at how this molecule reacts, the species that contributes electrons must attack from the backside. Molecular orbital theory predicts and supports that conclusion. That's nuts. We're drawing a bunch of balls and shapes and shady things, and you're telling me that random hand-wavy action actually describes reality? That's crazy, okay? But it does, and that's why it's cool, okay? And this is my horrible version of it, and it actually explains it, okay? Just imagine what happens when we actually have somebody that knows what they're talking about molecular orbital theory and explaining how those patterns come about. It's nuts, okay? But really, really cool. Don't stress a whole lot. We could spend a whole lot of time talking about it. It turns out it's not necessary because we can kind of shift and look a little bit more on the memorization side of it and some hand-wavy ways to kind of dodge knowing the hardcore orbital dynamics. Okay, with that, we are done with our molecular orbitals, and we're going to start moving into kind of physical properties in our next videos.